Good morning. Okay. The topic for today is energy and power. Most of the time this semester, up to now at least, we focused a lot on speed. Okay, we've been truly speed freaks, looking at how fast can we switch the signal, what does the time domain waveform look like. We've also looked at frequency responses of circuits. So this week we will spend on something a little bit different, and that relates to energy and power. Energy and power is getting a lot more gaining in importance in certainly this decade, and will do so in the future. And I'm going to work out a little example towards the end of the lecture, and there you will see that if you do things naively, your handheld devices, your cell phone and your laptops and so on, will just up and explode. Okay, you've got to be a little bit careful in terms of how to manage energy and power. Okay. Before I get into that, I just want to wrap up with a quick review of what we covered last week. So we ended last week by looking at positive feedback in analog circuits using an op-amp. And in particular, we built an oscillator. We built an oscillator that allowed us to charge a capacitor, and when the voltage across the capacitor equaled that at the minus terminal, it would flip and keep doing so. And at the output, you would get a waveform that looked like this. You would get a square wave output. Now, throughout the course, we've talked about getting square wave inputs. And this is one example of how you can actually produce a square wave. Okay, from pretty much from first principles, using a capacitor, resistors, and an op-amp. Now, I just want to wrap up this little item here by talking about one application of an oscillator. Okay, this application of the oscillator will really nicely close the loop on the body of knowledge relating to digital circuits that we've covered in this course. So what I want to talk about is, briefly, is a small digital system with a sender and a receiver. Okay, and the sender is sending a signal, receiver receives a signal. And in this course, we've talked about sender sending a sequence of ones and zeros. So say, for example, the sender wants to send some sort of a signal like this. Okay, we've seen that this is quite a legitimate signal. We get some kind of oscillatory behavior because of the inductance and capacitance associated with the wire. And what you've done is that you pretty much believed me when I've said that, well, this really corresponds to a 110. The sender wants to send a 110 signal to the receiver, and the receiver gets it. So this is a 1, this is a 1, this is a 0. But if I'm a receiver, okay, I'm going to look at the square wave. Okay, there's no such thing as sending a 1 on a wire. I mean, you can't send a 1 on a wire. You send a voltage signal or a current signal on a wire. Okay, so the receiver receives a voltage signal. It's going to be 0 for some time, and then maybe 5 volts or 3 volts or whatever is your high, and then 0 again. So how does my receiver know it's a 110? Why can't it be a 11111000? I mean, it doesn't know. Okay, so how does the receiver know it's a 110 sequence and not a 50 ones followed by 40 zeros? It doesn't know. So what we need is for senders to be able to communicate with receivers, we need some kind of agreed upon time when receivers sample the signal coming in and decide whether it's a 1 or a 0. Okay, they both have to agree on certain time bases when they look at the input. So one way to deal with this is I can have a clock, a square wave signal, which we call a clock in digital systems, and ship it to the other side in the following manner. Okay, so this clock signal can be applied to this sender and to this receiver. Okay, for more details on this, let me recommend page 735 of the course notes that talks about a detailed example of the use of a clock in a digital system. So what I can do is I can create a clock that looks like this square wave. A clock provides a notion of time to the circuit, and I have some kind of a clock signal generator, and I connect that to the sender and connect that to the receiver, and now both the receiver and the sender have a notion of time. And what I can do is I can tell my receiver, the sender and the receiver can have an agreement between them that says that look at the signal at your input when on the rising edge of the clock. Whenever the clock rises, whenever you see a rising edge, look at the value on the wire, and that's the value I sent. Okay? So by doing so, what I can do is that the receiver can look at the signal. At this rising edge, it sees a 0, if this is a VOH. Looks up here, sees a 1 here, sees a 1 here, and sees a 0. Okay, so it correctly samples 1, 1, 0 at the receiving end, and the sender can send the same sequence here once we have this time base. Okay, so this little brief foray into digital circuits was to simply give you an application of a circuit that can produce a square wave. Okay, I can create a clock with a time base. Also, interestingly, much more fundamental is we've looked at various abstractions throughout the course. Okay, we talked about discretizing space and looking at lumped signals. What I also want to point out is that a clock can be viewed as another fundamental abstraction in the digital domain, where what I'm doing is discretizing time. What I'm saying is that, look, in the digital domain, we've already discretized value, okay, into zeros and ones. Okay, but we still had continuous time until now. And what we do in digital systems is to say that, look, let's digitize everything, okay, or rather discretize everything, and let's discretize time as well into these points that happen on the rising edge of the clock, which means that the circuit has meaning, signals have meaning only when the clock is rising. Okay, that tends to discretize time, which means that I really don't care what happens to signals in this time, as long as on the rising edge of the clock, I get the right value. Okay, this concept is called discretizing time. Okay, and a clock lets you do that. All right, so remember that in digital systems, which you will learn about in 004, I'm really discretizing two things. Discretizing values into zeros and ones, and at the same time also discretizing time into a time when I sample things and a time when I ignore values on the wires. Okay, I think you will get to clocks in 6004 after about a month. So initially, you will just be focusing on the statics of the system without worrying about any dynamic clock introduced in the circuit. Okay, so that's just a brief little interlude, and with that, let me get into today's topic of energy and power. So why is this important? The reason this is important is that what really determines the size of your handheld? Okay, you may think, oh, it's electronics in the handheld. Okay, some of you may think, oh, the antenna in the handheld. Nope. Really, what really determines the size and weight of your handheld devices, your PDAs, your cell phones, your laptops, and so on, is by and large the battery. Okay, on page 2 of a little cartoon that shows you that if we did not have you learn about energy and power, that's what we would all be doing in order to use cell phones. Not surprisingly, the very first wireless phones ended up in automobiles, okay, because you had a big battery, and so you had these wireless phones only in cars. Because of a huge amount of research based on the knowledge, the technologies I'm going to talk about in today's lecture and Thursday's lecture, you will see very simple and elegant ways of reducing the amount of battery you need to be able to get some kind of function out of analog or digital devices. Okay? I also want you to take a look at page 2 of the handout that I've given you here, handout 63. This handout talks about the absolute latest in digital fabrication technology out there. Okay? This is not a paid commercial for IBM. So IBM has a technology called CU08. Okay, it's called Blue Logic, and it's called the copper 08 process. And in this process, IBM is, if you look down on page 1, for example, IBM claims that it can build up to 72 million gates in a single chip. Okay, with this technology, they're able to build 70 to 80 million gates, where a gate is, unless otherwise mentioned, pretty much defined as a 2-input NAND gate equivalent. Okay, so your inverter, your NAND gate, and so on count as a gate. And they can build up to 80 million, close to 80 million of these little suckers on a single chip. Just imagine that. And each chip is on the order, the biggest chip they can build is on the order of 18 to 19 millimeters on a side, roughly 2 centimeters on a side. Okay, so on a chip that's about 1 square inch, you can plonk down 80 million gates. What's more important for today is what's on page 2, actually. So I've circled 2 things on page 2. One thing that I've circled is power supply range in the 0.7 to 1.3 volts. Notice that voltage, the power supply voltage for these chips, is significantly lower than the 5 volts that we've been nominally talking about in this course. Okay, when in doubt, our problems have used 5 volts. But notice that in this technology, they're talking about using voltages for the power supply, VS, in the range of 0.7 to 1.3. So why is it so much lower? Well, we'll find out. The second thing I've circled is something called power dissipation. Okay, and you say power dissipation is said to be 0.006 microwatts per megahertz per gate. Okay, so it says power dissipation is 6 nanowatts per megahertz per gate. Okay, so what they've said is that each gate of your circuit will dissipate this much power at a 1 megahertz frequency. And what the implication of that is that you should be able to convert that single number to the power dissipation in any chip that you might build, depending on the number of gates that you have, the frequency you run the circuit at, the voltage that you use, and so on and so forth. Okay, by the end of today's lecture, you will be able to take this number and parlay that into the power dissipation of your of any chip that you might want to build with this. Okay, so that just serves as a motivation that by the end of this lecture, you will understand, how to very quickly, in 5 seconds or less, boom, given a chip. So yeah, that should consume about 30 watts of power. Okay, and what we'll also do is, based on some examples here, estimate the power of not the Pentium 4, but a chip following the Pentium 4, let's call it the Pentium 5, would consume if it ran at 1 gigahertz. Okay, and we will come up with some absolutely shocking numbers based on what you have learned. Okay, so with that kind of motivation, let me get into talking about, do some theory, and get into the foundations of energy and power. Let's get to page 3. So to drive the theoretical discussion, I would like to focus on the energy dissipated in a MOSFET gate. Okay? And fundamentally, it will talk about looking at energy and power in circuits containing switches, resistors, and capacitors. Okay? The MOSFET gate is simply an illustrative example to drive the theory. But fundamentally, what I'm going to show you, or lead you through today, will tell you how to compute the power and energy when you have capacitors, resistors, and voltage sources and switches in your circuit. So, so we'll look at a circuit that looks like this. Your vanilla inverter circuit. So my inverter, I apply some V in signal here. It could be a square wave. It could be some sequence of ones and zeros. And this is the inverter that we all know and love. And this guy here is I've stuck in a capacitor here. And this capacitor is meant to model the input gate capacitance of whatever this inverter drives, plus any capacitance of the wire leading up to that gate, and so on. So it's just a lumped capacitor that I've stuck on there. So I'm interested in determining a few things. One is what we call the standby power. Okay, you will see all these terms being used in cell phones and so on. In your cell phone manufacturer gives you two numbers. Okay, of course, both are over exaggerations, but they give you two numbers nonetheless. One number is the number of days that the cell phone battery will last when in standby mode, right? That's exactly where standby comes from. Okay, so in standby mode, how much power does your cell phone, or how long will the battery last? That's the standby power. And the second thing is what we call active use power. Active use is when you are making a phone call and so on. What is the power consumed? And then again, your manufacturer of your cell phone will give you a much smaller number for the active use power of your cell phone. So what I'm going to do is assume for the power for discussion that the inverter is driven by a square wave signal of the following sort. So this is Vin. And I would drive this with a signal of this sort. The period applied at the input. So I'm switching the inverter on and off, on and off, on and off, okay? And T1 seconds for the high, T2 seconds for the low, okay? So this is the inverter, and this is the input signal, and we'll keep coming back to that again and again. Okay. So rather than directly taking this circuit and analyzing its power, I would like to do things a little bit in a slightly roundabout manner. What I'd like to do is show you some very simple circuits, okay, and analyze their standby and active powers, and then show you that this circuit simply is a combination of some of the simple things that you have seen. So example one. So example one, I would like to take a simple circuit that looks like this. A voltage source V applied to across a resistor R, some current I. Okay, and if I apply a voltage across this resistor, that voltage will simply appear across the resistor. And the power is simply given by VI, which is simply V squared divided by R. Okay, this is 6002101 in the very first chapter. That's the power that is dissipated by this resistor, simply V squared divided by R. That's the power dissipated by the resistor. Okay, where does that power come from? That power the voltage source supplies the power. So this guy here supplies this power, and this guy here dissipates it. What is the energy that I dissipate in time t? Remember, power is the rate of energy dissipation. And so energy is simply power multiplied by time. So for a circuit like this, energy dissipated in time t is simply VIT. Okay? So for our gate, remember we have two situations. We have Vs, we have RL, we have Ron, VO, and Vin. So Vin is high. If Vn is high with respect to ground, then Ron, the switch is on, and this is the circuit that I see. And in this situation, the power consumed is simply V squared divided by the resistance here. So it's simply Vs squared divided by RL plus Ron. Okay, let me mark that with an asterisk. I will refer to this later. Similarly, when Vin is low, the MOSFET is off. And the power is simply 0. I have no current flowing down, and the power is 0. Okay, absolutely basic stuff. Okay, absolutely basic. So the power, when I have the MOSFET on, for the kind of inverters you've seen so far, this is the power consumed by the inverter. Okay, and this asterisk here is simply to say, hold that thought. We will get back to it a little later. Let me work out a second example. In the second example, I'd like to consider the following circuit. A voltage source Vs, and with a strange arrangement of switches, S1, with a resistance R1, a capacitor C in this manner, a switch S2, and a resistor R2. For now, don't worry about how the circuit comes about. Just assume that I've drawn the circuit for you. And what I want to do is compute the power under certain conditions. Notice that if this is off and this is off, okay, there's no current flowing either in this loop or this loop, and the power consumed, dissipated by the circuit is 0. Okay, but there are some arrangement of switches for which I do consume power. And so let me show you that arrangement of switches. And what I'm going to do is assume that the switch is open and close with the following periodic cycle. Okay, let's assume that when this is high, S1 is closed, and S2 is open. And when this is low, assume that S1 is open, S2 is closed, and let's assume this is T, this is T1, this is T2. Okay, that sequence should be reminiscent of this input that I'm feeding to this inverter. So all I'm telling you here is that I'm giving you the circuit. I want to compute the power consumption of the circuit. And what I'm telling you is that with the frequency of with a time period of capital T, for the first T1 seconds, this switch is closed and that is open. So this circuit applies. In the second half of the clock, this switch is open, so this circuit applies. Okay? And what I'm interested in finding out is what is the energy dissipated in each cycle of time capital T. And I also want to find out the average power. Okay? So just spend about 5 seconds staring at this and kind of intuit what's going on here. So I start by putting a voltage source here, and I close the switch, ka-chunk. That's open. So start by closing this. So what happens? When I close the switch, Vs is going to charge up this capacitor, right? So I get current flowing through my resistor. So I'm going to be charging up this capacitor here. Okay? And then, let's say I allow T1 to be as large as possible. And so this capacitor is going to be charged up to all of Vs. So after a long time, this guy gets to be Vs on the capacitor. And as it's charging up, I have current flow through the resistor, so it's sitting there dissipating power. Notice that this sucker does not dissipate energy, it simply stores energy. So the energy supplied by the voltage source comes in, some of it gets stored in the capacitor, and some of it is being dissipated by the resistor. That gets me to the end of T1. At the end of T2, I open this switch and close this switch. When I close this switch, I have some energy on the capacitor, and that's begin to, and the voltage across the capacitor begins to drive a current through this resistor R2. And now the capacitor supplies its stored energy, and its stored energy then begins to dissipate through resistor R2. And if T2 is very long, then all the charge in the capacitor drains out, and the voltage on the capacitor at the end will be 0. So that's just sort of a high-level description of what goes on. And now let's go ahead and compute from first principles the energetics of this little circuit. So let's look at the entire period capital T. And as a first step, look at T1. Okay? And so when T1 is in place, S1 is closed, and S2 is open. Accordingly, the circuit that applies looks like this. Vs, S1 is closed. So that's closed. And I have this resistance R1. I have this capacitance C, some voltage Vc across the capacitor. Okay, you can go ahead and assume that Vc of 0 is 0, that I start off my life with no charge, with no voltage across the capacitor. Okay. So first of all, let me plot the waveforms and write the expressions down, and then compute the energy supplied by the voltage source. Okay, and then look at where the energy goes. So you all know, or should know by now, if I plot Vc as a function of time, okay, remember this is really easy to do. The Vc as a function of time goes like this. At time t equal to 0, I'm telling you that the capacitor voltage is 0. Okay, I'm telling you that. Okay, so it's at 0. And then the capacitor charges up until it reaches Vs. Okay, so I also know that after a long time, this will be Vs. Okay, after a long time, that will be Vs. And between those two, I have a rising function that looks like this. I can similarly plot the current for you. At time t equal to 0, instantaneously the capacitor looks like a short. And so the current that I start off with is going to be Vs divided by R1. Okay, the voltage across the capacitor is 0. So all that voltage falls across the resistor R1. So Vs divided by R1 is the initial instantaneous current. And after a long time, because Vc reaches Vs, the current is going to be 0. Okay, and between those 2 points, I get an exponential decay. I can very quickly write down the expression for the current, and that is simply the initial value, Vs divided by R1, okay, times the exponential decay minus t divided by the time constant for the circuit, R1C. Okay, so you've seen this stuff before. Here comes the part that we care about for now. Let's find out what is the total energy provided by the source. When dealing with energy computations, you have to be incredibly careful of these words here. Supplied, provided, okay, versus dissipated. Okay, so dissipated implies that the resistor is burning energy. Provided means that the source is supplying that energy. So energy provided by source during T1. Okay, let's go ahead and compute that very quickly. So the energy supplied by the source is simply the voltage across the source multiplied by the current being supplied by the source. This is I. Remember, by associated variables convention, if I have a voltage across some element and the current into the element is positive, okay, then that element dissipates power. Okay? If the voltage here is, say, 1 volt and it's supplying current, if the I is out in the other direction, then it is supplying power. So in this case, the current I is going to be on the outside, heading outside. So total energy is going to be the instantaneous power integrated over time, and so and that's simply Vs. Remember, the instantaneous power is Vs times the current I. Okay, so the instantaneous power is simply Vs times I. That's the instantaneous power. So to get the energy provided by source in some time, I have to integrate that instantaneous power over the period of interest T1. Okay, that gives me the energy supplied by the source during T1. And let me go ahead and substitute for I with this expression here. Okay, so it's Vs times I. And I is Vs divided by R1 times this expression here. So that gives me Vs squared divided by R1, e to the minus t R1c dt. Okay? So let me carry out the integration there, and I get minus 1 by RC. Okay, so I get this outside. And I also get to write down, oops. Let me do that a little bit more carefully. So Vs squared by R1 simply comes out, and I get a minus R1c in the numerator. Remember, if I differentiate it, then I get R1c in the denominator. So for the integral, that comes up here. And then I write down e to the minus t divided by R1c to 0 and t1. Okay, so this R1 and this R1 cancel out. And I end up getting something that looks like this. I get C Vs squared. Okay, and so here, there's a minus sign out here. So at 0, this thing goes to a 1. So I get a 1. And because of the minus sign, I get e to the minus t1 R1c. Okay, all I've done here is simply go through the math to do this integration here. What I'm also going to do is assume that if T1, if the time that the switch is closed is much, much bigger than the time constant of the circuit. Okay, so if T1 is much, much greater than R1C. Okay, if this is much, much greater than R1C, then this term goes to 0. And this becomes more or less equal to C Vs squared. What do we have here? What we have here is that if I let the switch stay closed for a long time and S2 be open, then the voltage is going to supply some amount, the voltage source is going to supply some amount of energy. Okay? That energy will equal CVS squared. So the voltage across the capacitor will be Vs, and all that energy would have been supplied by this guy. So let me pose the following conundrum here. So if the voltage across the capacitor is Vs, we know the energy stored in the capacitor is half CV squared. So the energy in the capacitor is half C Vs squared. At the end of the day, since the voltage across the capacitor is Vs, half CVS squared is the energy stored here. But we know from this calculation, the source has supplied CVS squared. So the source has supplied twice that energy. Okay, so this guy has supplied twice that energy, and only half of that is stored here. Okay, so who ate up the other half? The resistor, exactly. Okay, so the resistor has walloped half the energy. Okay, so let me just show it to you. So dissipated half CVS squared. It's pretty interesting. It's a pretty simple result. If T1 is very large compared to the time constant, then half the energy is on the capacitor, and half of it has been burned by R1. Okay, this energy hasn't been burned. It is simply stored. Okay, it's stored by the capacitor. Okay. And if you do a simple energy conservation arithmetic here, the energy dissipated in the resistor plus that stored in the capacitor equals the energy supplied by the source. Okay? All right, let's go to T2 now. At T2, S2 is closed and S1 is open. Let's look at the second part of the cycle when S1 is open and S2 is closed. And what's going to happen now is the left-hand part of the circuit can be ignored, and I can focus on this part. So S2 is closed. This is R2, my capacitor. This is VC. This is the circuit of interest. So what's the initial condition on this? What is the value of VC initially? So start off, because remember, I allowed this capacitor to charge up fully, and so initially I have Vs on the capacitor. And so the energy on the capacitor initially is half C Vs squared. That's the energy on the capacitor. This time around, I won't go through an integration process like that, but you can if you like, and do it in a much simpler manner to say that now, let's suppose that T2 is much greater than this time constant. If T2 is much greater than R2C, this time constant. So if that time is much greater, then this entire, the initial voltage Vs, okay, drives a current through the resistor, and after some amount of time, the voltage across the capacitor goes to 0. Okay, and all the energy in the capacitor gets dissipated in R. Okay, so if T2 is much greater than R2C, then energy dissipated in R2 is simply half C Vs squared. So notice that the energy dissipated in R1 in the first half cycle is half C Vs squared. And the second half cycle, during T2, if T2 is large enough, all this energy gets dissipated in this resistor R2. And I have that expression here. Okay, so let me just so let me say that this is E1, and let me say that this is E2. So E1 is dissipated in the resistor, and E2 is dissipated in R2 in the second half cycle. So a couple of interesting things to note at this point. One is that E1 and E2 are independent of R. Okay? If the time constant is small enough compared to the time that I charge the capacitor, then half the energy gets lost in the resistor, and that is simply half CVS squared. And if I let this discharge completely, it doesn't matter what resistor I'm discharging it through. That's the intuition. If I have certain energy here, and I let it discharge completely, it doesn't matter what this resistor is. Small or high, large, doesn't matter. All this energy gets dissipated there. Okay? The rate at which the energy gets dissipated will change depending on R2. If R2 is very small, then I get a burst of power initially and then a rapid decay after that. But if R2 is very large, then I have a much slower release of energy. But suffice it to say that the energy dissipated, the total energy in T2 is simply half CVS squared. All right. So let's put T1 and T2 together and look at the total energy dissipated, total energy dissipated. E is simply E1 plus E2. Okay, dissipated in each cycle. Assuming T1 and T2 are much larger than the respective time constants. Okay, and I know that this is half CVS squared, so this is simply CV squared. So if I have an arrangement of switches and capacitors like that, I charge the capacitor, discharge the capacitor. Charge the capacitor, discharge the capacitor. What it's saying is that in a charge-discharge cycle, I'm using up CVS squared of energy. Half CVS squared when I charge it up, and half CVS squared when I discharge it. That's what I get. Let's compute the average power. Okay, the average power dissipated, P average, in a cycle is simply E divided by T, where T is the period of my of the square wave sequence that I've shown you out there. So this is simply CVS squared divided by T. So if the period of the square wave is capital T, I can express that as a frequency. Let's say, for example, the period of the square wave is T. So let's say the frequency of the square wave is simply 1 by T. Okay? So I can also express this as C Vs squared F. So what does this say? Let me mark that as thing to remember. The second thing to remember. One was the power that was the static power. And second is this power relating to this frequency F and the charging and discharging of the capacitor in that little circuit shown up there. So this average power is CVS squared F. What this is saying is that if F is high, if I have high frequency of charging and discharging the capacitor, then I'm charging and discharging much more frequently, so I'm going to consume more power. Okay, notice that at any given time, there is no direct connection between the power supply and the ground. What I'm doing is my capacitor is an intermediary. I'm dumping some charge in the capacitor, and the capacitor dumping the charge into ground. Okay? It behaves like a switched capacitor. And what it's doing is it's being charged and discharged at frequency F. So it makes sense that the amount of current that average current pumping that I'm pumping through relates to the frequency at which I'm charging and discharging the capacitor. And similarly, the average power also relates to the value of the capacitor. If C is larger, I dissipate more energy. And same way with the voltage. If the voltage is higher, then the power in that period, or the average power, relates to Vs squared. So spend a few seconds staring at the two expressions. This power here, relating to just this connection between the power supply and ground, and that power out there relating to charging and discharging capacitors. So let's get back to our inverter right now. So this is our inverter circuit. And let us say that I drive the input with the waveform shown here. Okay, well, I go back to the same situation as here. Okay, I drive the input with a square wave with T1 and T2 as the high time and the low time. The equivalent circuit for this is not exactly what we saw there, but the equivalent circuit for this will look like this. I have a Vs, okay, and the Vs supply is connected through RL. Vs connected through RL to a capacitor C. Okay, this is my voltage V0. So Vs is always connected to ground through this resistor and capacitor in this manner. And then I have a resistor here, R-on, corresponding to that MOSFET. And there I am switching it on and off in a way that it's on during T1 and off during T2. Okay, so the situation here is a bit different from that simple situation I computed there. So much like I computed the power dissipation in that circuit, I can go ahead and compute the total power dissipated in this circuit. Okay, I won't do it here. The algebra tends to be a bit more grubbier than what I've been through. And suffice it to say that you can show that the average power is given by Vs squared to RL plus R on plus C Vs squared F RL squared okay, and for details, I suggest that you look at section 12.3 of the course notes. So section 12.3 goes through the algebra to compute the total power dissipated by this circuit, by this specific circuit, and here's the expression we get. Okay, and let's take the specific situation where RL is much greater than Ron. If RL is much greater than Ron, then I can ignore this Ron here. Okay, and I get this. And out here, if I ignore Ron, then RL and RL cancel out, and I get CVS squared F. So if I ignore Ron compared to RL, this is the expression I get. Okay? Now you can see why I went through those two examples. This is exactly the power consumed by the connection between power supply and ground. And this CV squared F is the power consumed in charging and discharging the capacitor. If you look at the circuit here, it's consuming two kinds of power. One kind of power is due to the current flowing directly from VS through RL and Ron to ground. Okay? Oh, this also assumes, by the way, this assumes that T1 is equal to T2. Okay? So up in this circuit, there are two kinds of power. One is the power when the switch is on and I have a current flowing from VS to RL to ground. Okay, notice I get an extra factor of 2 in the denominator here. And that 2 comes about because the connection to ground only happens half the time. Okay, it's half that power out there because I'm connected to ground only when the switch is on. And that happens only half the time. And so therefore, I get the VS squared divided by 2R1. And then CVS squared F is simply the power that I consume because I'm charging and discharging the capacitor C. Okay, so notice that in this inverter circuit, there are two kinds of power. One is called the standby power, which is the static power being consumed by the circuit. And the second power is the dynamic power because of the circuit switching up and down. This relates to the star, and this relates to the double star. And to demonstrate that, I have a little demonstration here that has an inverter, and I'm going to up the frequency of the square wave driving the inverter. I'm going to show you a few numbers, so hang on for 2 minutes after this demo. I'll give you some numbers, and I want you to go ahead and compute the numbers based on what we've seen here. And you will get suitably impressed, I promise you. So this is the input fed to the inverter. This is the output of the inverter. Notice that the output of the inverter reflects some sort of an RC time constant because of the output driving the capacitor in the same way here. So I start off by showing you that on the left-hand side, I show you I'm simply measuring the power being consumed by the circuit. I notice that the power being consumed is expressed by the needle being at this point here. So this is a very low frequency. So this is almost all standby power, okay, consumed by the inverter. All right? So the inverter is on half the time, and when it's on, it's consuming power. So what I'm going to do now is increase the frequency. As I increase the frequency driving the inverter, what should happen to this needle? So as I increase the frequency there, that waveform should become closer and closer together. And what should happen to the needle? That should begin to go up. So as I increase the frequency, it should consume more and more power, and the needle should start going up. So let me do that for you. So it's, in terms of numbers there, it's on top of the 4 on the scale in the middle. So I'm going to increase the frequency very slowly. Unfortunately, the sampling scope messes up the waveform, so ignore the waveform for now. Just look at the meter as I increase the frequency. Okay, notice that I've increased the frequency by about a factor of 2 or 3. And notice here that this meter has moved, the needle has moved to the right. And I can keep doing that, and the needle keeps moving to the right as I'm consuming more and more power because I'm driving the inverter faster and faster and faster. Okay? So that should convince you that there is a standby power, and there's some power component related to frequency. This relates to your standby power in your cell phone. This relates to active use. So let me show you some numbers, and you can plug those numbers in yourself and see how much power this inverter is going to consume, and see if it makes sense. So assume that I have a chip with 10 to the 8 gates. F is 1 gigahertz, that's 10 to the 9. Assume C is 0.1 femtofarads, which is 10 to the minus 16 farads. Assume Vs is 5 volts. Assume RL is 10 kilo ohms. Okay, use these numbers. Plug these numbers in here and get a sense if our modern day circuitry used that inverter, okay, what would be the power consumed by a chip that contains 10 to the 8 of these gates? Okay, you will find out that you may have to use a nuclear power reactor to actually drive that chip. But go check it out for yourselves. In the next lecture, we will see then how do our cell phones work? How does life go on, despite this horrendous calculation here?